The cosmos around us appears vast and eternal. Every star, every planet, and every atom you are made of exists within a stable framework of reality, a set of rules we call physics. But what if that framework is a lie? What if our universe is resting on a foundation of quantum quicksand, waiting for a single random event to erase it completely? This is not science fiction. This is the terrifying possibility known as vacuum decay. By the end of this exploration, you will understand the physics of how a bubble of nothing could rewrite the cosmos. We will uncover why our existence might be more fragile than we ever dreamed, and what a silent, light-speed wall of new physics would mean for everything we know. How does it feel to live in a universe that could simply change its mind? That stable framework of reality is built upon a concept we think we understand, but quantum physics reveals a far stranger truth. To grasp how the universe could erase itself, we first need to redefine what we mean by nothing. In our everyday lives, a vacuum is simply empty space, the absence of air and matter. But in the quantum realm, empty is the wrong word entirely. Imagine the most perfect void you can think of, a region of space utterly devoid of atoms, light, and dust. Even there, at the smallest scales, reality is not calm. It is a frenzied, bubbling sea of activity known as the quantum foam. This is not a metaphor. According to the laws of quantum mechanics, pairs of virtual particles and their antiparticles are constantly flickering into existence, borrowing energy from the vacuum itself for a fleeting instant before annihilating each other and vanishing. It is a ceaseless dance of creation and destruction happening everywhere all the time, even in the space between the stars. This seething background activity is what physicists call the true vacuum state. It is not empty. It is the lowest energy configuration that the various fields of the universe, like the electromagnetic field or the Higgs field, can settle into. Think of it like a ball resting peacefully at the very bottom of a deep valley. The valley floor represents this lowest energy state, the quantum vacuum. The ball is stable there, content. This is our universe as we know it, with all its familiar forces and particles. But what if that valley is not the only one? What if, beyond the hill we are sitting in, there exists a deeper, steeper valley we cannot see? That is the unsettling question at the heart of vacuum decay. Our entire reality is built on the assumption that our ball is at the absolute bottom. But if a deeper valley exists, then our universe is not in its true, ultimate ground state. We are living in what scientists call a false vacuum, a state of precarious, temporary stability. It is as if our universe is a frozen lake, perfectly solid and reliable on the surface, while beneath, unimaginable currents churn in the darkness. The ice holds for now, but the possibility of a crack, a trigger that sends everything plunging into the depths below, is a shadow on the edge of our understanding. This false vacuum scenario finds its most concrete and chilling form within a field you have likely heard of, the Higgs field. You may know it as the thing that gives particles mass, but its true nature is far more profound. The Higgs field is not just a property of matter. It is an invisible energy field that fills every cubic centimeter of the universe, a kind of cosmic molasses that particles must swim through. The resistance they experience as they move is what we perceive as mass, but the stability of this field, and thus the stability of mass itself, hinges on a delicate quantum shape physicists call the Mexican hat potential. Picture, if you will, the broad brim of a sombrero. Now flip that hat upside down so the crown points downward, creating a central hill with a depressed ring around it. This three-dimensional shape is the classic model for the Higgs field's potential energy. The very bottom of that depressed ring, the lowest point, is where the field naturally wants to settle. That is the true vacuum, the absolute lowest energy state. But our universe, according to our best measurements, is not sitting in that trough. Instead, we seem to be perched on the central peak, right at the top of that little hill in the middle of the ring. From our perspective, it feels like a stable plateau. The ball is not rolling because it is balanced perfectly at the summit. This is our false vacuum. We exist in a universe where the Higgs field has a value that is not zero, giving particles the masses we observe, but this value may not be the final, most stable one. It is as if the entire cosmos is a marble carefully balanced on the rim of a wine glass. It looks steady, it feels solid. For all of human history, it has remained perfectly in place. But the laws of physics tell us there is a lower energy state available, the bottom of the glass itself. All it would take is one tiny quantum nudge to send that marble and our entire reality tumbling down into a new and unknown configuration. This precarious position on the brim of the hat is the seed from which the nightmare of vacuum decay grows. Our universe, then, may not be a frozen lake, but something even more deceptive. It could be a state physicists call metastable. This is a special kind of stability, one that is real and durable but ultimately temporary. Think of a pencil balanced perfectly on its tip. With no disturbance, it can remain upright indefinitely. It is stable against small breezes, but it is not in its most natural, lowest energy state, which is lying flat on the table. A single, random vibration from a passing truck could be enough to topple it. Our cosmos has been that pencil for 13.8 billion years, a staggering span of time that gives us an illusion of permanence. Or consider a supercooled liquid. You can chill water well below its normal freezing point, and if it is perfectly still and pure, it will remain a liquid. It looks like water, acts like water, but it is in a precarious state. Drop in a single speck of dust or give the container a gentle tap, and the entire volume will flash freeze into solid ice in an instant. Our universe might be that supercooled water, existing in a liquid state when, by all rights, it should have crystallized into something else eons ago. This is not wild speculation. It emerges as a genuine prediction when we plug our best measurements, like the mass of the Higgs boson, into the equations of our most successful theory of reality, the standard model of particle physics. The math suggests the valley we are sitting in might have a false bottom. We appear to be in a shallow depression on a hillside, not in the deepest valley in the landscape. The ball is not rolling because the walls around our little divot are high enough to contain it for now, but the terrain beyond our dip slopes downward to a far lower point. This metastable condition sets the stage for a cosmic transition of unimaginable consequence. If our universe can find a path to that lower state, it will take it. The question is not if such a transition is possible, but what could possibly trigger it. The trigger for this cosmic rewrite would not be a cosmic collision or a supernova's fury. It would be a whisper from the quantum realm, an event so subtle it defies our everyday intuition. This process is called quantum tunneling, and it is the key that could unlock the end. In our macroscopic world, if you roll a ball toward a hill, it needs enough energy to climb over the top to reach the other side. If it does not, it simply rolls back. This is classical physics, but in the bizarre domain of quantum mechanics, particles play by different rules. An electron, for instance, can sometimes simply appear on the other side of an energy barrier, as if it vanished from one location and instantly materialized in another. It did not go over the hill, it tunneled straight through it. This is not a theory. It is a proven, measurable phenomenon essential to how the sun shines and how modern electronics work. Now apply this principle to the Higgs field and our precarious position on the brim of that cosmic hat. The hill surrounding our false vacuum is an energy barrier, a wall of instability that keeps our universe in its current, familiar state. But through quantum tunneling, a random fluctuation could cause a microscopic speck of space, perhaps smaller than an atom, to spontaneously transition to the true vacuum state. In that instant, a bubble of a new reality would be born. It would be as if the marble balanced on the wine-glass rim through sheer quantum chance suddenly found itself inside the glass, resting at the true bottom. This bubble would not contain stars or galaxies. It would be a region where the Higgs field has settled into its absolute lowest energy configuration, rewriting the very laws of physics within its boundary. The rules of this new vacuum would be alien and absolute. The forces that hold atoms together, the very concept of mass as we know it, could cease to exist or transform into something unrecognizable. This microscopic nucleation event, happening at a random point in the vast emptiness between galaxies, would be the first domino to fall in a chain reaction that consumes the cosmos. The moment this bubble forms would be utterly silent and invisible. At the instant of its quantum birth, it would be a sphere of new physics smaller than a proton, a microscopic flaw in the fabric of our reality. Within that vanishingly tiny volume, the Higgs field has completed its tunnel through the energy barrier. It has settled into its true lowest valley, a state of vacuum energy so profound it makes our universe seem like a chaotic, high-energy frenzy by comparison. The rules inside are not just tweaked, they are rewritten from the ground up. The fundamental constants that dictate the strength of gravity or the binding force of atomic nuclei could have entirely new values. Particles as we know them, electrons and quarks, might not even exist in this new vacuum. Their masses, which are set by the old Higgs field value, could be zero or infinite or something entirely unfamiliar. This is not merely a new planet with different chemistry. It is a new kind of existence with a different operating system for reality itself. Think of it like a single pixel on your screen suddenly switching from the code for a vibrant blue to the code for a color your monitor cannot even display. That pixel is now governed by a different set of instructions alien to every pixel around it. This bubble is that pixel, but for the cosmos. Its initial size is laughably insignificant, a quantum speck against the backdrop of 100 billion galaxies. Yet within that speck lies a potential so destructive it defies comprehension, because this new vacuum is not content to stay small. The bubble would not remain a harmless curiosity. Its very existence creates a fundamental instability at the boundary between two different realities. The true vacuum inside the bubble is a state of lower energy, a deeper valley in the cosmic landscape. Our false vacuum universe outside is by comparison a higher energy state. In physics, systems always seek the lowest possible energy, like water flowing downhill. This creates an immense pressure difference at the bubble's spherical wall. The lower energy true vacuum exerts an irresistible pull, causing the wall to expand outward with ferocious speed. It accelerates to nearly the speed of light in an instant, becoming a spherical shockwave of pure transformation. This is not a wall of stone or metal. It is a propagating front of fundamental change, a ripple in the fabric of space-time where the rules of existence are being rewritten. Think of it like a flame front in a field of dry grass. The unburned grass represents our high-energy false vacuum. The ash behind the flame is the new, lower-energy true vacuum. The fire consumes the grass not out of malice, but because the ash is a more stable, lower-energy state. The flame front expands, converting everything in its path, releasing the stored energy of the grass as heat and light. The bubble wall operates on a cosmic scale, but the principle is eerily similar. As it expands, it does not push our universe aside. It converts it. Every atom, every force field, every law of physics that the wall touches is instantly rewritten into the new, alien configuration of the true vacuum. The energy difference between the old state and the new state is titanic, and it is released at the wall. This makes the expanding boundary a shell of inconceivable energy, a luminous ring of annihilation that radiates with the fury of a billion supernova. This is the erasure front. It does not destroy matter in an explosion. It does something far more absolute. It changes the definition of matter itself. A star in its path would not be vaporized. It would simply cease to be a star as the very particles composing it lose their properties and dissolve into the new, fundamental substrate of the true vacuum. The universe behind the wall is not a ruined version of our own. It is a different reality altogether, one where our history, our physics, and our very concept of existence are rendered null and void. The moment the bubble wall arrives, there is no warning. No alarm sounds across the galaxy, no tremor in the fabric of space. For any observer, the end of their universe would be both instantaneous and incomprehensible. The wall itself is a boundary of pure transition, a razor-thin shell moving at the speed of light. From one nanosecond to the next, every fundamental rule that governs existence is swapped out for a new set. The strength of the electromagnetic force, which dictates how atoms bond to form molecules, could suddenly become 1,000 times weaker or 1,000,000 times stronger. The strong nuclear force, the glue that holds atomic nuclei together against their own repulsion, might simply flicker out of existence. In that instant, the delicate balance that took billions of years to forge stars and planets is erased. An atom of carbon, the very basis of organic life, does not get torn apart. Instead, the forces that define what an atom is cease to apply. The protons and neutrons in its nucleus, no longer bound by the familiar rules, would simply drift apart or reconfigure into exotic particles that cannot form stable matter. Electrons would either vanish or lose their properties, dissolving the intricate electron clouds that give atoms their chemical identity. The transformation is not a violent disintegration. It is a silent, fundamental obsolescence. The universe does not scream, it forgets. Picture a distant, living world in the path of this wall. From the perspective of a being on its surface, the sky would suddenly be filled with an impossible, blinding light, the radiant energy released at the conversion front. But there is no time to perceive it. Before the light from that wall could even travel the distance to their eyes and be processed by their brain, the wall itself has already passed through them. Their body, their planet, their sun are all converted in the same absolute moment. Their neurons, their memories, the very atoms that composed their thoughts are rewritten into the new physics of the true vacuum. They do not die because death is a biological process that requires the old laws of chemistry to have meaning. They simply cease to be as the concept of being itself is redefined. A star does not explode. It winks out of existence not because its fuel is exhausted, but because nuclear fusion, the process of stars, is no longer a physical possibility under the new constants. The planets orbiting it are not shattered into debris. They are unmade, their rocky silicates and metallic cores dissolving into a formless quantum soup governed by alien principles. This new reality behind the wall is likely a barren, simplistic state. The complex structures that arise from our specific balance of forces, structures like galaxies, nebulae, and living cells, almost certainly cannot form there. It is a cosmic blank slate, a uniform sea of low-energy fields where the rich tapestry of our universe is not just destroyed, but rendered permanently impossible. The erasure is total, final, and silent. This brings us to a deeply unsettling and practical question. Could we see it coming? Is there any warning system we could build, any scientific instrument that might give us a heads-up before the end of reality? The answer, grounded in our current understanding of physics, is a profound and chilling no. The very nature of the event makes it the ultimate stealth attack. Since the bubble wall expands at the speed of light, or perhaps even faster if space-time itself is rewritten, the first sign of its existence would be the wall itself. There is no signal that can outrun it. No beam of light, no ripple of gravity, no ghostly neutrino could arrive ahead of it to tell us what is coming. Information itself is bound by the cosmic speed limit. The wall is both the event and the announcement of the event, arriving in the same instant. One moment, the telescope shows a familiar starfield. The next, an impossible wall of light and transformation is upon us. and by the time our instruments register it, our entire solar system is already being rewritten. This leads to the most haunting implication of all. It could have already begun. Somewhere in the vast darkness between the galaxies, perhaps billions of light years away, a random quantum fluctuation may have already triggered the nucleation of a true vacuum bubble. That sphere of new physics could be expanding right now, at this very moment, on a direct path to erase the Milky Way, and we would have absolutely no way of knowing. The event horizon of this bubble is not like a black hole which warps space and gives clues to its presence. It is a silent, light-speed revision of the rules, invisible until it strikes. We are left peering into a cosmos that might already be doomed, living in the brief and ignorant calm before a storm we cannot detect. Our entire history, from the first stars to this very thought, could exist in the shrinking island of the old universe, surrounded by an advancing tide of absolute change that has already sealed our fate. The cosmos offers no farewell, but the speed of light may not be the final word on how fast the end can travel. There is a terrifying nuance to this physics that suggests the bubble wall could move even faster, making the event not just unstoppable, but truly instantaneous from our perspective. We are taught that nothing can travel faster than light through space. This cosmic speed limit is a cornerstone of Einstein's relativity, and it applies to all matter and information. But the bubble wall is not an object moving through space-time. It is something far more fundamental. It is a phase change in the fabric of reality itself, a reconfiguration of the vacuum's ground state. Think of it like the moment ice forms in that supercooled water. The crystallization front moves through the liquid, but it is not a thing swimming in the water. It is the water itself changing state. The speed of that front is governed by the properties of water and ice, not by the speed limit of ripples on the water's surface. In cosmology, we already know space-time itself can expand faster than light. During the universe's first fraction of a second, a period called cosmic inflation, the fabric of space expanded at a rate so prodigious that regions were pushed apart faster than light could ever hope to connect them. This is not a violation of relativity because it is space itself that is stretching. Nothing is moving through space faster than light. Space is creating more space between points. The bubble wall's expansion could operate on a similar, devastating principle. As the true vacuum forms, it establishes a new set of physical laws, and those new laws dictate the properties of the space-time within it. If this new vacuum state permits or even encourages a different kind of expansion, the wall could propagate as a shock wave in the definition of space, not just across it. It would be less like a wall rushing toward you and more like the entire concept of here and there being rewritten at a pace that outruns causality itself. If this is possible, then the warning we thought we might not get shrinks from zero to something even less than zero. There would be no wall of light approaching. One moment our universe exists, the next it does not. The transition would be a discontinuity in time. A hard cut from one reality to the next with no interval in between to perceive, measure, or comprehend. The cosmic surprise attack would have no front line. It would simply be everywhere at once. This scientific nightmare is not a fringe idea. It is a serious, ongoing calculation at the very forefront of physics. The question of whether our universe sits in a false vacuum is not answered by philosophy, but by numbers, specifically the measured masses of two fundamental particles. The first is the Higgs boson itself, the particle associated with the Higgs field. Its mass, discovered at the Large Hadron Collider to be about 125 billion electron volts, is one crucial input. The second is the top quark, the heaviest known elementary particle. When physicists plug these two numbers into the immensely complex equations of the Standard Model and map out the resulting cosmic energy landscape, the shape of that metaphorical hat becomes terrifyingly clear. For our universe to be absolutely stable, sitting in the true lowest valley, the brim of that hat would need to curve upward at the edges, creating a protective barrier. But the current best fit numbers suggest the brim might actually curve downward. Our valley, in this calculation, has no containing wall. It is a shallow depression on a slope that leads to an abyss. The ball is not moving because the slope is incredibly gentle, and 13.8 billion years has not been enough time for a random quantum jostle to start its roll. This is the metastability result. It means our cosmos is not eternal. It has an expiration date, albeit one that could be trillions upon trillions of years in the future. The physicist who helped pioneer this calculation, Joseph Licken, has stated plainly that the data suggests we are in a metastable state. It is a conclusion that emerges directly from our most successful theory of reality. Yet the story does not end there, because the standard model is almost certainly incomplete. The calculation of vacuum stability sits on a knife's edge, exquisitely sensitive to the precise values we use. A tiny shift in the mass of the top quark or the Higgs boson, well within the current margins of experimental error, could flip the result. If the top quark were just a fraction lighter, the math often tips back toward absolute stability, placing our universe safely in a deep, eternal valley. This uncertainty is why leading physicists like Gian Giudis describe the vacuum stability condition as balancing on a tightrope. We are measuring the mass of a speck of dust to determine the ultimate fate of a cathedral. Furthermore, the standard model itself ignores gravity. When we try to incorporate the effects of gravity at the highest energies, the picture becomes even murkier. New particles or forces predicted by theories beyond the standard model, like those involved in supersymmetry, could completely reshape the energy landscape, potentially providing the stabilizing barrier that our current math says is missing. This is the heart of the scientific debate. One camp looks at the numbers and sees a genuine, long-term existential risk written into the laws of physics. Another camp argues that the inclusion of new physics will inevitably restore stability, that nature would not be so precarious. The truth is, we simply do not know yet. Every new run of the Large Hadron Collider, every more precise measurement of these fundamental masses, is not just an exercise in particle physics. It is a diagnostic on the longevity of reality itself. We are, in a very real sense, taking the universe's vital signs to see if it is terminally ill. The debate is alive, rigorous, and profoundly consequential, reminding us that the greatest mysteries are not always in the distant cosmos, but encoded in the fabric of everything around us. The ultimate timeline for this cosmic reset is not written in any calendar. Vacuum decay does not follow a schedule or a countdown clock. Its arrival is governed by the cold, random mathematics of quantum probability. In any given cubic centimeter of space, at any given moment, the chance that the Higgs field will tunnel into the true vacuum is unimaginably small. Physicists calculate this probability, and the numbers they arrive with are so astronomically tiny they defy human comprehension. The expected timescale for such an event to occur in a volume the size of our observable universe could be longer than 10 to the power of 100 years. That is a 1 followed by 100 zeros, a time span so vast it makes the current age of the universe, a mere 13.8 billion years, seem like a single blink in an endless eternity. In any practical, human sense, this means it will effectively never happen. The universe will likely die a heat death, with stars burning out and matter decaying, long before a vacuum decay bubble spontaneously appears. Yet the word probability holds a terrifying double meaning. While the odds are infinitesimal per second per cubic meter, they are never zero. This is the essence of the quantum lottery. The universe is not rolling a single die. It is conducting a continuous, frantic experiment in every minuscule fragment of space and time, everywhere, all at once. Think of it like buying a lottery ticket. The odds of any single ticket winning the grand prize are vanishingly small. so small you can confidently plan your life assuming you will not win. But someone, somewhere, eventually does win. The universe is playing a version of this game with an infinite number of tickets being drawn every instant. The jackpot is the nucleation of a true vacuum bubble. Given enough time, and the universe has an incomprehensible amount of it, this random quantum fluctuation becomes not just possible but statistically inevitable. This creates a bizarre duality in our cosmic prognosis. On a timescale of quintillions of years, vacuum decay might be an inescapable fate, the final quietus for a metastable cosmos. But from our fleeting human perspective, perched in a tiny sliver of cosmic time, it exists in a state of pure, unsettling maybe. It is a threat that combines long-term inevitability with immediate, total unpredictability. The bubble that rewrites reality could form 1 billion years from now in a galaxy far, far away. Or through sheer, monstrously bad luck, it could have already begun forming yesterday in the void between Andromeda and the Milky Way. We live suspended in that profound uncertainty, in a universe that is both astonishingly stable for our purposes and fundamentally unstable in its ultimate nature. The bubble, once born, does not stop. It is a self-perpetuating cosmic event, a chain reaction with the entire universe as its fuel. Driven by the immense energy difference between the false vacuum and the true one, its wall accelerates outward, destined to expand forever. There is no force in our physics that can contain it, no barrier of stars or dark matter that can slow its advance. It will simply keep converting space, rewriting the rules, until it has consumed every last corner of the cosmos it can reach. The process might take eons, crossing the unimaginable gulfs between galaxy clusters, but the outcome is absolute. Our familiar universe, in all its splendid complexity, would be entirely replaced by a uniform sea of this new alien vacuum. The great cosmic story of stars, planets, and life would have its final page written not with a whimper, but with a silent, fundamental revision. Could the end come from more than one direction? Absolutely, quantum tunneling is a random process, and if it can happen once in the vastness of space, it can happen again elsewhere at any time. We might not face a single expanding bubble, but a multitude of them. Picture a pot of water just beginning to boil. Tiny steam bubbles nucleate at random points on the bottom, each growing and rising. In the cosmic version, true vacuum bubbles could spontaneously appear in different, unconnected regions of the universe. Each would be its own sphere of new physics, expanding at nearly the speed of light. They would grow, and eventually their boundaries would meet. When two of these all-consuming walls collide, they would merge. The energy released in that collision would be beyond apocalyptic, but it would be a footnote in a story already concluded. The result is a chaotic, growing foam of new vacuum domains, a patchwork quilt of alien realities stitching itself together over the corpse of our old universe. For any structure caught in the gaps between these bubbles, the end would arrive from multiple horizons at once, a closing pincer of transformation. The final state is not a diverse new cosmos. It is a sterile simplicity. Our universe is rich and structured precisely because its vacuum state has a certain energy, which gives rise to the specific forces and particles we know. The true vacuum, by definition, is a lower energy configuration. In almost every plausible scenario, that means a much less interesting one. The forces that allow for complex chemistry, the nuclear interactions that forge elements in stars, the very existence of stable matter itself, these are features of our particular, perhaps accidental, vacuum. The new reality would likely lack the conditions for any of it. It might be a perfectly uniform void, empty not just of stars, but of the very potential to ever form them again. All the intricate patterns woven over billions of years, from the spin of a galaxy to the beat of a heart, are not just erased, they are rendered permanently impossible, their blueprints thrown away. The cosmic canvas is not painted over with a new picture. it is replaced with a blank sheet of a different material, one that cannot hold any image at all. So we are left with a haunting vision of the far future, not the gentle fading of heat death where the last embers of stars cool over incomprehensible spans of time, but a more abrupt and absolute conclusion. An expanding sphere or a network of them, silently rewriting the operating system of reality as it goes. From our perspective within this fragile island of familiar physics, the process would be both inevitable and invisible until the very last instant. The entire epic of our cosmos, from the Big Bang to this very moment, exists in a bubble of its own, a bubble of temporary stability in a quantum landscape that may favor a deeper, quieter state. Our existence is not threatened by a cataclysm within the universe, but by the universe itself deciding to become something else entirely. And in that decision, every memory, every discovery, and every unanswered question would find not an answer but an end. Yet this silent erasure is not the only way our universe could end. Cosmology paints several other portraits of cosmic doom, each with its own unique flavor of finality. There is the Big Crunch, a dramatic reversal of the Big Bang where the expansion of space finally halts, succumbs to gravity, and pulls everything back together into a singular, fiery point of infinite density. It is a cosmic collapse, a violent reunion of all matter and energy. Then there is the Big Rip, a more recent and eerie possibility. If a mysterious force called dark energy grows stronger over time, it could eventually overcome every binding force in nature. First, galaxies will be torn from each other, then stars from their galaxies, planets from their stars, and finally, atoms themselves would be ripped apart, leaving a universe of lonely, shredded particles drifting in an ever-accelerating void. And of course, there is the classic heat death, the long, slow fade. In this scenario, the universe expands forever, stars burn out, black holes evaporate, and all energy differences gradually smooth out into a uniform, lukewarm sea of particles. It is a death by entropy where no work can be done, no structure can form, and the cosmos reaches a state of permanent, featureless equilibrium. Vacuum decay stands apart from all of these. The Big Crunch and the Big Rip are about the dynamics of spacetime itself, either collapsing inward or stretching apart with catastrophic force. Heat death is about the gradual exhaustion of usable energy within the existing rules of physics. Vacuum decay is none of these. It does not crush space, rip it apart, or slowly cool it down. Instead, it changes the rulebook that space and everything within it must obey. It is not a physical catastrophe happening within the universe. It is a metaphysical shift of the universe. Think of the other scenarios as different ways a magnificent clock could stop. The gears could rust into place over eons, the spring could snap violently, or the entire mechanism could be smashed with a hammer. Vacuum decay is different. It is as if, in an instant, the very law of gravity that makes the pendulum swing is silently repealed. The clock does not break. The concept of clock itself ceases to have meaning. This distinction makes vacuum decay uniquely absolute. In a heat death, the information that once made up a galaxy or a living thought might still, in principle, exist in the quantum states of those scattered particles, even if it is forever inaccessible. In a Big Rip or Crunch, there is at least a dramatic physical process, a story with a final, explosive chapter. Vacuum decay offers no such narrative. It is a quiet, instantaneous edit. It does not destroy structures, it redefines what structure is allowed to be. The universe does not become cold, dark, or torn. It becomes other. It transitions to a state where the history that came before is not just over, but rendered physically impossible to have ever occurred under the new regime. This is why physicists often regard it as one of the most final endpoints conceivable. The other doomsdays leave behind a corpse, however scattered or dense. Vacuum decay leaves behind a different universe entirely, one where our past is not a memory etched into the cosmos, but a forgotten dream written in a language that no longer exists. This profound uncertainty forces us to look beyond our cosmic horizon. Our telescopes show us a universe stretching 13.8 billion light-years in every direction, but that is merely the observable part, the light that has had time to reach us. The true extent of all that exists could be infinite, and if space goes on forever, then the implications for vacuum decay become mind-bending. In an infinite cosmos, every possible quantum event, no matter how improbable, is not just likely. It is guaranteed to happen somewhere an infinite number of times. This means that if our vacuum is metastable, then the spontaneous formation of a true vacuum bubble is not a singular future threat. It is a constant, ongoing process happening right now in realms we can never see. Somewhere beyond the reach of our most powerful instruments, a bubble of new physics may have already nucleated and begun its unstoppable expansion. Another may have popped into existence 1 trillion years ago and consumed an entire supercluster of galaxies. In an infinite universe, these catastrophic events are not rare. They are ceaseless. Our local group of galaxies, our Milky Way, might simply reside in a fortunate, stable pocket that has not yet been touched by the advancing walls of transformation. We could be living on a stable island in a stormy sea of constantly rewriting realities. This idea stretches further into the concept of the multiverse. Many leading cosmological theories, like eternal inflation, suggest our Big Bang was just one bubble of stable space inflating within a much vaster, more chaotic meta-universe. In that primordial froth, countless other bubbles would have formed, each with its own random set of physical laws and constants. Some of those bubble universes might have landed in a deep, stable vacuum valley. Others might have been born metastable like ours. In that grand multiversal picture, vacuum decay is not an end. It is a process. A metastable bubble universe could, at any moment, find a lower energy state and trigger a new bubble within itself, a cosmic Russian doll of phase transitions. Our entire reality, then, might be nested inside an older one, and it could one day spawn a new, stranger reality within it. This leads to a humbling philosophical shift. Our physics, with its precise strengths for gravity and electromagnetism, its specific particle masses, is not necessarily special or eternal. It might just be a temporary configuration, a random roll of the quantum dice that happened to produce a universe complex enough to ask questions about itself. The laws we consider fundamental and unchanging could be merely local bylaws relevant only to our island of stability. They are not written in stone for the cosmos. They are written in sand, waiting for the tide. This transforms our place in existence. We are not inhabitants of a permanent, orderly universe, but temporary residents in a fleeting eddy of stability within a much wilder, more dynamic and perhaps dangerous cosmic landscape. The quiet night sky with its familiar constellations is not a promise of permanence. It is a snapshot of a moment in a much longer, stranger story, most of which we are forever cut off from witnessing. Our science, for all its power, can only describe the rules of our local bubble. The ultimate nature of reality may be a churning ocean of different rules, where universes with different physics bloom and vanish like bubbles in a boiling pot. We are left to wonder if our island is truly safe, or if we are simply enjoying the calm before a light-speed tide we cannot yet see finally reaches our shores. This profound uncertainty leads us to a powerful and strangely comforting thought. The very fact that you are listening to this, that we are here contemplating cosmic doom, might itself be a clue to the universe's nature. This idea is known as the anthropic principle. In its simplest form, it states that the universe we observe must be compatible with the existence of observers. It sounds almost trivial, but its implications for vacuum decay are profound. If our cosmic vacuum were wildly unstable, prone to decaying in its first few million years, then complex structures like galaxies, stars, and planets would never have had time to form. Life and conscious beings to wonder about it would be impossible. The fact that we are here 13.8 billion years after the Big Bang asking these very questions tells us something crucial. Our local patch of the cosmos, at the very least, has remained metastably frozen long enough for all the intricate processes of cosmic evolution to unfold. Our observation acts as a kind of cosmic selection bias. We can only find ourselves in a universe that has not yet decayed. It is like a survivor of a shipwreck wondering why they ended up on the one piece of driftwood that stayed afloat. The driftwood's buoyancy isn't a lucky accident from the survivor's perspective. It is a prerequisite for their existence to even pose the question. So our presence is a data point. It suggests that while vacuum decay may be a genuine threat in the long-term future, the probability of it happening in any given century must be incredibly low, low enough to allow for a multi-billion-year window of stability. The anthropic principle doesn't prove we are safe forever. It simply explains why we wouldn't be around to worry if we weren't. It frames our entire reality with its specific laws and constants, not as a guaranteed outcome, but as one possibility among many that just happen to be hospitable. We are not living in a specially designed or perfectly stable universe. We are living in one that is stable enough for long enough to have allowed us to emerge and look back at it. This shifts the question from why hasn't it happened yet to what does our existence tell us about the timescales involved? Our very consciousness becomes evidence against an imminent universe-wide decay. Yet the principle offers no guarantees for tomorrow. It only explains the past. The bubble could still form 1,000 years from now or 1 billion. Our observation selects for a history without decay, but it cannot select for a future without it. We are the products of cosmic luck so far, living on borrowed time in a universe that may have an expiration date we simply haven't reached. That lingering fear of a cosmic reset button is not just theoretical. It has at times erupted into public panic with a very specific target. When the world's most powerful particle accelerator, the Large Hadron Collider, was first switched on, headlines screamed about the possibility of creating microscopic black holes or strangelets that could destroy the Earth. Lurking among those fears was a quieter, more profound dread. Could smashing particles together at nearly the speed of light provide that quantum nudge, triggering the vacuum decay bubble right here in our own backyard? The question is terrifyingly logical. We are, after all, using a machine to probe the very forces that govern reality, to recreate energies not seen since the first moments of the Big Bang. It feels like we are poking a sleeping dragon with a very sharp scientific stick. The scientific community's response to this fear, however, is not dismissive. It is grounded in a powerful and reassuring piece of evidence that has been running a far more extreme experiment since time began. The energies produced inside the Large Hadron Collider's detectors are staggering by human standards trillions of electron volts. But to the universe, they are a gentle breeze. For billions of years, our planet, our solar system, and every corner of our galaxy have been continuously bombarded by cosmic rays. These are not rays of light, but atomic nuclei, mostly protons, that have been accelerated to energies far beyond anything we can create in a lab. The most powerful cosmic rays, dubbed "oh my god" particles, carry the kinetic energy of a professionally thrown baseball, all packed into a single subatomic particle. They strike our atmosphere with energies millions of times greater than what the Large Hadron Collider can achieve. These ultra-high-energy collisions have been happening naturally, relentlessly, all across the cosmos since the first stars formed. They are the universe's own permanent particle accelerator, operating at energies we can only dream of replicating. And here is the crucial point. If the Higgs field were so unstable that a collision at Large Hadron Collider energies could tip it into the true vacuum, then one of these vastly more powerful cosmic ray strikes would have done so eons ago. The fact that we are still here, that the universe has survived this constant, natural barrage of ultra-high-energy experiments, is the most compelling evidence that our vacuum is not that fragile. The Large Hadron Collider is not playing with fire we have never seen. It is studying a flame that has been burning safely in nature's fireplace for the entire history of life. This perspective transforms the machine from a potential trigger of doom into our most precise window into stability itself. Its true role in this cosmic drama is not to end the universe, but to help us read its vital signs with unprecedented clarity. By measuring the properties of the Higgs boson and other particles with exquisite precision, the collider is allowing us to map the shape of that cosmic energy landscape. Each new data point helps us calculate with less uncertainty whether the valley we live in has sturdy walls or a dangerous downward slope. It is a tool for diagnosis, not destruction. The fear of accidentally causing vacuum decay speaks to a deep human anxiety about tampering with forces we do not fully understand. Yet nature, in its grand and indifferent experiment, has already conducted the ultimate stress test. Our most powerful machines are merely whispers compared to the cosmic shouts that have echoed through the void since the beginning. This does not eliminate the long-term quantum threat, but it firmly removes the blame from human curiosity. The universe's stability, however temporary, has already weathered far greater storms. But the story of our universe's fate is not written in stone by the Standard Model alone. That framework, for all its success, is known to be incomplete. It cannot explain gravity, the existence of dark matter, or the nature of dark energy. This incompleteness is our greatest source of hope. There are compelling theories that extend physics beyond the Standard Model, and many of them carry the potential to rescue our cosmos from metastability. The most prominent of these is a concept known as supersymmetry, often called SUSY. It proposes a beautiful, symmetrical relationship between the two fundamental classes of particles, fermions, which make up matter, and bosons, which carry forces. For every known particle, every electron, every quark, every photon, supersymmetry predicts a hidden superpartner. An electron would have a selectron, a quark would have a squark, and so on. These superpartners have never been observed, suggesting they must be incredibly massive, perhaps only appearing at the extreme energies of the early universe or inside powerful colliders. Why does this matter for vacuum decay? Because these hypothetical superpartners would contribute to the quantum froth that shapes the energy landscape of the Higgs field. In the intricate mathematics of vacuum stability, the top quark, due to its enormous mass, plays an outsized role in pushing the brim of that cosmic hat downward toward instability. The superpartners of the top quark, however, would exert an opposing influence. Their presence in the equations could act as a counterweight, pulling the brim back upward and creating a sturdy barrier around our valley. If supersymmetry is real, and if these particles have the right properties, our universe could transition from being metastable to being absolutely stable, resting eternally in the deepest possible valley. The vacuum decay threat would vanish, not because we misunderstood the probability, but because we corrected the map of reality itself. Discovering evidence for SUSY would be more than a new chapter in physics. It would be a cosmic reassurance, a sign that the fundamental rules are not just temporary but eternally anchored. Other theoretical extensions offer similar hope. The idea of a grand unified theory, which merges the electromagnetic, weak, and strong nuclear forces into a single, elegant framework, often introduces new fields and particles that could also stabilize the vacuum. Even the mysterious properties of dark energy or the quantum nature of gravity, once understood, might reveal stabilizing mechanisms hidden in the fabric of spacetime. Each of these frontiers represents a possible rewrite of the vacuum stability calculation. The current result, which places us on a knife's edge, is based on an incomplete picture. Adding new pieces to the cosmic puzzle could dramatically change the final image. It is like trying to judge the stability of a chair by only looking at 3 of its legs. The fourth leg, hidden from view, might be solid and strong, making the chair perfectly safe. Our current physics is that partial view. The full theory, when we find it, may show that all four legs are firmly planted. This search is not philosophical. It is the driving mission of experimental physics for the 21st century. The Large Hadron Collider and its future successors are not just hunting for new particles for curiosity's sake. They are conducting a forensic investigation into the structural integrity of reality. Every unexplored energy range, every analysis of collision debris is a test for the signatures of these stabilizing theories. The absence of evidence so far is not evidence of absence. It simply tells us that if these superpartners or other new physics exist, they are heavier or more elusive than we once hoped, waiting for more powerful machines to reveal them. So, the existential dread of a silent cosmic erasure is balanced by a profound and active scientific hope. The same human curiosity that conceived of vacuum decay is now tirelessly working to prove it impossible. We are not passive inhabitants of a fragile universe. We are its investigators, using the laws of physics to diagnose its long-term health. The outcome of this search remains unknown, hanging in the balance between a terrifying quantum possibility and a more comforting eternal stability. Our fate rests not on a random fluctuation, but on the true, yet-to-be-discovered shape of the cosmic landscape. The silence left behind by the bubble is not just an absence of matter, but a potential erasure of meaning. If every atom and every law is rewritten, what happens to the information that defined our universe? Information in physics is not just data in a book. It is the specific arrangement of particles that makes a star different from a nebula or a memory different from a random thought. It is the blueprint of reality itself. So when the wall of true vacuum converts a galaxy, does it simply delete this cosmic blueprint? The question strikes at the heart of whether anything of our universe could, in any sense, survive. This is not merely philosophical. It connects directly to one of the most profound puzzles in modern physics, the black hole information paradox. Black holes, according to Einstein's general relativity, are perfect traps. Their gravity is so intense that not even light can escape. If you throw a book, a computer, or an entire planet into a black hole, it vanishes behind the event horizon, seemingly lost forever. This presented a crisis because the laws of quantum mechanics state that information can never be truly destroyed. It can be scrambled, hidden, or transformed, but the universe must always keep a kind of quantum ledger. For decades, physicists like Stephen Hawking wrestled with this contradiction. Hawking's own work suggested black holes could evaporate over eons, leaving behind only a faint thermal radiation, seemingly devoid of any information about what fell in. This implied a fundamental violation, a paradox where the universe forgets. The resolution, which is still being explored, suggests the information is not destroyed. It is preserved in unimaginably scrambled form on the surface of the event horizon, or encoded in the Hawking radiation itself. The black hole does not erase the ledger. It encrypts it. Now apply this thinking to vacuum decay. The bubble wall is an event horizon of a different kind. It is a boundary beyond which our physics no longer applies. Anything that crosses is subject to a new set of rules. If information must be preserved, as quantum mechanics insists, then the detailed data of our universe, the position of every atom in every star, the text of every book ever written, the pattern of every thought must somehow be translated into the language of the new vacuum. But this is where our physics hits a wall. We have no theory that can describe such a translation. The information might be preserved in some abstract mathematical sense, encoded in the structure of the bubble wall or the quantum state of the new vacuum, but it would be utterly inaccessible and unrecognizable. It would be like taking a masterpiece painting, reducing it to its raw atomic elements, and then using those atoms to make a brick. The information of the atoms is preserved, but the painting is gone forever. The story it told, the beauty it held, is lost in the transformation. The true vacuum likely lacks the complex structures, like atoms and forces, necessary to represent that information in any meaningful way. So from our perspective, from the perspective of any structure that depends on our specific physics, the information is effectively annihilated. The universe does not remember. It reformats the hard drive. This leads us to an even deeper layer. The very concept of information as we understand it is a product of our particular vacuum. In a reality with different fundamental forces and particles, information itself might be something entirely different. What we call a memory or a galaxy might correspond to no coherent structure in the new physics. Our history becomes not just encrypted data, but data written in a programming language that no longer runs on the new cosmic computer. The paradox forces us to confront the nature of reality. Is the universe fundamentally a collection of things, or is it a flow of information? If it is the latter, then vacuum decay might be the ultimate corruption of that data stream. We are left with a haunting thought. Perhaps the only universes that can ever be observed, the only ones that can contain complex observers who ask these questions, are those where information can be stably stored and processed over cosmic timescales. A universe that undergoes vacuum decay early in its history fails that test. It never gets to tell its story. Our ability to ponder this erasure, then, might be the universe's own, fleeting way of bearing witness to itself before the silence returns. This cosmic silence has not gone unnoticed by storytellers and thinkers. The chilling idea of vacuum decay has begun to seep from physics papers into our collective imagination, appearing in novels, games, and films as the ultimate existential threat. In Liu Cixin's monumental science fiction trilogy, The Three-Body Problem, a central terror is the concept that the universe's fundamental laws are not sacred. Civilizations can weaponize physics itself, altering the speed of light or the behavior of matter to make regions of space uninhabitable for others. This echoes the vacuum decay premise that reality's rules are local, changeable, and terrifyingly fragile. The universe becomes a dark forest where every civilization hides, fearful that revealing its location might invite an attack that rewrites the physics of its home. Here, the bubble is not a random quantum event, but a deliberate act of cosmic war, a reset button pressed by an unseen enemy. The game False Vacuum takes the concept more directly, tasking the player with understanding and perhaps preventing this ultimate catastrophe. These narratives tap into a deep-seated fear far beyond asteroids or supernovas. It is the fear of uncreation, of a blank slate that does not just end life, but erases the very canvas upon which life was painted. Philosophically, this moves us into profound and unsettling territory. Vacuum decay presents a form of cosmic nihilism that is almost impossible to grapple with. Traditional nihilism suggests that human endeavors lack inherent meaning in a vast, indifferent universe, but vacuum decay proposes something more absolute. It suggests that the universe itself lacks inherent, permanent meaning. All structure, all history, all the emergent beauty and complexity from galaxies to consciousness could be a temporary accident, a local fluctuation in a field that prefers a state of featureless simplicity. It is the ultimate argument for insignificance, not just of our species, but of our entire physical reality. Compared to this, a black hole or a heat death feels almost comforting. They are endings that happen within a consistent set of rules. Vacuum decay is the ending of the rules themselves. It tells us that the story we are part of might not just have a final page, but that the entire alphabet used to write it could be declared obsolete at any moment. And yet, there is a powerful, defiant counterpoint to this nihilism. The very act of contemplating vacuum decay, of using mathematics and colossal machines to probe the stability of reality, is a profound testament to the opposite of insignificance. It is the human drive to understand, to look into the abyss and map its contours, even if the map reveals our own potential doom. This curiosity is not negated by the fragility it uncovers, it is highlighted by it. We are the universe in one small corner, becoming aware of its own possible instability. That self-awareness, that relentless questioning, creates its own meaning within the temporary bubble of stability we inhabit. Philosophers have long wrestled with the idea of finding purpose in a finite existence. Vacuum decay simply scales that finitude to the cosmic level. It does not erase the love, the art, the discoveries, or the connections made during our brief window of stable physics. If anything, it intensifies them. Knowing the ice could be thin makes every step upon it more deliberate, more precious. Our search for a complete theory of physics, for signs of supersymmetry or other stabilizing principles, is not just science. It is a form of cosmic hope, a wager that the universe is not only knowable but enduring. We are, in a sense, placing a bet on meaning itself. The silence of the true vacuum may be the ultimate end, but the conversation we are having right now, in this fleeting moment of complex physics, is the universe arguing for its own significance. And that argument, whispered against the backdrop of infinite silence, is perhaps the most human thing of all. The sky would not darken, it would change. One moment, the constellations hang in their familiar patterns, a tapestry of distant suns. The next, from a single point on the celestial sphere, a new kind of dawn erupts. It is not the warm glow of sunrise, but a cold, shimmering wall of impossible light. It is iridescent, like a soap bubble the size of the cosmos, reflecting colors that have no name in our spectrum. This wall is perfectly geometric, a razor-straight arc of transformation slicing across the heavens, and it is utterly silent. There is no roar, no cosmic wind, no tremor in the ground. The only sound is the pounding of your own heart, because the event outruns its own noise. It moves at the speed of causality itself, a frontier where reality is being rewritten faster than any signal of its approach could warn you. You are not watching an object approach, you are witnessing the horizon of existence itself draw nearer. The wall is not made of energy or matter as we know it. It is the visible manifestation of new laws being imposed upon the old, a luminous scar where the universe is stitching itself into a new pattern. As it grows, swallowing more of the sky, the familiar stars at its edge do not simply vanish. They distort. Their light stretches into smears of impossible color, like paint dropped into water, before dissolving into geometric patterns that hurt the mind to perceive crystalline lattices and fractal spirals that belong to no natural order. The world around you begins to feel wrong. The blue of the sky near the wall shifts toward a purple that feels metallic, then into a green that carries the scent of ozone and something else, something alien. The shadows cast by trees no longer fall in straight lines. They bend, twist, and begin to crawl across the ground as the very behavior of light is reprogrammed. You look at your own hand, and for a fleeting instant you see the spaces between the atoms. The solidity of your body becomes a suggestion, a temporary consensus of forces that is being voted out of existence. There is no pain, there is only a profound and accelerating dislocation, a feeling that every anchor of perception is being cut loose, the wall is upon you. The silent, shimmering curtain of light fills your entire field of vision, and in that final nanosecond, perception itself breaks down, color becomes sound. Shape becomes temperature, memory becomes a physical texture that unravels, the concept of you, a pattern of information bound by specific chemical and electrical rules, meets a universe that no longer supports those rules. There is no flash of white, no tunnel of light. There is a translation, an instant of incomprehensible reconfiguration, as every particle in your body, every synaptic connection that housed a thought or a memory, is seamlessly converted into the new, fundamental substrate of the true vacuum. From a human perspective, it is over in less than a blink. The horror of vacuum decay is not in its violence but in its silent, surgical precision. It does not destroy the painting. It declares that paint, canvas, and the very idea of images are no longer valid concepts. And in that declaration, the entire masterpiece of our reality simply ceases to be. That final, silent translation from one reality to another may be the ultimate fate, but science refuses to accept it as an unanswerable mystery. We are left with a profound and practical challenge. How do you test for the end of everything? This is not like predicting a storm or an asteroid impact. We cannot recreate a universe-ending bubble in a laboratory, and if we saw one coming in the cosmos, it would already be here. The search for evidence becomes a cosmic detective story, one where the clues are not in the sky, but in the most precise measurements we can possibly make. The first and most crucial line of inquiry is to refine the map of that cosmic energy landscape. Every decimal point matters. Teams at the Large Hadron Collider and other facilities around the world are engaged in a relentless campaign to measure the masses of the Higgs boson and the top quark with ever greater precision. Think of it as surveying the exact shape of the valley we live in. Is the ground beneath us truly sloping downward, or is it perfectly flat? A tiny shift in the measured mass of the top quark, even by an amount smaller than the current margin of error, could tip the calculation from metastability to absolute stability. These are not abstract numbers, they are vital signs for reality itself. Each new, more accurate measurement is like taking the universe's temperature again, hoping the fever of instability breaks. The next generation of particle colliders, already on the drawing boards, is designed with this existential diagnosis in mind. Their primary goal is to measure the Higgs boson's properties with such exquisite detail that we can finally know, beyond reasonable doubt, whether our valley has sturdy walls or a dangerous cliff edge. This is indirect evidence, but it is powerful. It is like studying the composition of ice to determine if a frozen lake is stable enough to hold your weight, without ever needing to step onto it and risk falling through. Alongside this, physicists are hunting for the fingerprints of new physics that could stabilize the vacuum. The ongoing searches for supersymmetric particles or other exotic entities at colliders are not just about completing a theoretical checklist. They are a direct hunt for the missing architectural supports that might be holding up our cosmic home. Finding a selectron or a squark would be more than a discovery. It would be a relief. It would mean the equations have a stabilizing term we have not yet seen, a hidden buttress in the foundation. If these particles are found, the nightmare of vacuum decay could vanish from our equations, replaced by a picture of long-term cosmic security. But the laboratory is not our only source of clues. We might also look for echoes of the past. Cosmologists meticulously study the afterglow of the Big Bang, the cosmic microwave background. This faint radiation is a snapshot of the infant universe, and its subtle patterns hold secrets about the universe's earliest moments. Some theories suggest that if our vacuum is metastable, it might have undergone similar but localized phase transitions in its first fiery instance. These quantum bubbles, if they formed and collided in the primordial chaos, could have left faint, circular imprints or specific patterns of polarization in the microwave background, cosmic bruises from ancient brushes with a different state of reality. Searching for these bizarre signatures is like an archaeologist sifting through ancient ash, looking for the footprint of a cataclysm that almost was. It is a long shot, but it turns the entire sky into a fossil record of stability. So the ultimate experiment is multifaceted and immense. It is a global effort spanning colossal machines, space telescopes, and theoretical calculations of breathtaking complexity. We are testing the fabric of existence by weighing its fundamental pieces and listening for whispers from its birth. The stakes could not be higher, for a positive result in one direction tells us we live on borrowed time, while a result in the other could grant us a form of cosmic peace. This detective story has no final chapter yet, only the relentless turning of pages by thousands of scientists, each measurement a new line in a narrative about whether our universe is a permanent home or merely a temporary shelter in an infinite storm. Does this knowledge burden us or set us free? There is an undeniable weight to learning that reality itself might be built on a fragile premise, a cosmic secret that, once known, cannot be forgotten. This leads to a difficult ethical question. If the probability of vacuum decay is unimaginably small, and its arrival would be completely unstoppable and undetectable, is there any real value in discussing it publicly? Does broadcasting this doomsday scenario do anything other than seed a deep, unproductive anxiety, a background hum of existential dread that serves no purpose? It is a fair concern. We carefully consider the psychological impact of other threats, from climate change to pandemics, balancing alarm with actionable hope. But here, there is no action to take. No bunker can protect you from a rewrite of physics. No government policy can stabilize the Higgs field. The threat, while scientifically valid, offers us no lever to pull, no button to push. In that light, talking about it can feel like cosmic fear-mongering, an exercise in highlighting a terrifying possibility solely for the sake of the shudder it provokes. Some might argue that this knowledge should remain within the specialized halls of theoretical physics, a technical footnote in papers filled with equations, because bringing it into the public sphere only spreads a paralyzing sense of helplessness. Why burden people with a doom they can neither prevent nor prepare for? This perspective prioritizes psychological comfort over raw, unsettling truth. It suggests that some mysteries, especially those of an existential magnitude, are better left unexamined by the general public. Yet there is a profound counterargument, one rooted in the very essence of what it means to be a conscious species in a vast universe. Scientific transparency is not a convenience, it is a cornerstone of an enlightened society. Hiding a scientific concept because it is frightening is a form of paternalism that undermines trust and treats the public as children unable to handle complex truth. The pursuit of understanding, no matter where it leads, is a core human endeavor. We climb down from the trees to look at the stars, not to avoid looking at them. Knowing that our universe may be metastable is not useless information. It is a monumental piece of the puzzle of what we are and where we live. It transforms our cosmic context. We are no longer just inhabitants of a planet orbiting a star. We are temporary residents in a fleeting eddy of stable physics, a rare and perhaps precious oasis of complexity in a wider landscape that may favor simplicity. This knowledge does not have to lead to nihilism. It can lead to a radical and profound appreciation, understanding that our stable physics, and thus our very existence, is not guaranteed, forces a powerful shift in perspective. It makes every moment, every connection, every discovery within this temporary bubble not less meaningful, but infinitely more so. The love you feel, the art you create, the curiosity that drives you to learn, these are not trivial happenings in an eternal, indifferent universe. They are brilliant, temporary flames burning against an immense and silent dark. They are the universe in our small corner, experiencing itself in a state of glorious, fragile complexity. To know the ice is thin is to walk upon it with greater care, not to curse the journey. Talking about vacuum decay, then, is not about spreading fear. It is about completing the map of reality, even if the map shows a cliff at the edge. It is an exercise in cosmic honesty. It confronts us with our true scale and our true situation, stripping away illusions of permanence. That confrontation is uncomfortable, but it is also the source of our deepest wisdom and our most genuine awe. The value is not in preparing for an end we cannot stop, but in fully understanding the nature of the stage upon which our entire story is performed. The silence of the true vacuum may be the ultimate end, but the conversation we are having here and now, in this fleeting sliver of cosmic time, is the universe arguing passionately for its own significance. And that is a conversation worth having, no matter how it ends. This cosmic uncertainty is not a new kind of fear for humanity. We have always lived with existential risks. Our ancestors huddled in caves, knowing a storm or a predator could end everything. Later, we learned that plagues could sweep continents and asteroids have scarred our planet. Today, we manage the global risks of climate change and pandemic. These threats are terrifying, but they share a crucial feature. They happen within the universe. We can, in theory, see them coming, understand their mechanisms, and sometimes even fight back. Vacuum decay is different. It is a threat to the arena itself, a risk that the very rules of the game could be silently repealed. There is no fighting it, there is no preparing. This knowledge can feel like the ultimate form of helplessness, a shadow that makes all other fears seem quaint. How do you live with a shadow that vast? The answer may not lie in looking for an escape, but in changing how we see the ground beneath our feet. This profound uncertainty does not have to be a prison. It can be the key to a deeper kind of freedom. Consider the most precious moments of your life. The warmth of a shared laugh, the quiet beauty of a sunset, the thrill of learning something new. None of those moments are made less real or less meaningful by the potential instability of the Higgs field. In fact, their value is thrown into stark, breathtaking relief. They are not trivial events in an eternal, guaranteed universe. They are brilliant flashes of complexity and connection in a temporary oasis of stability. They are the universe through us experiencing something rare and fleeting. Knowing the ice is thin does not mean we should stop skating. It means we should cherish every glide, every turn, every moment of balance with a new and profound intensity. This perspective transforms the cosmic dread into a form of radical gratitude. Our ability to even conceive of vacuum decay is itself a miracle. It required billions of years of cosmic evolution to forge stars, planets, and the complex chemistry of life. It required the rise of consciousness, the development of language, and the slow, relentless build of science over centuries. That a collection of atoms arranged in just the right way can look up at the night sky and not only wonder about the stars but calculate the potential instability of the very fabric holding them together is astonishing. We are the universe thinking about itself, diagnosing its own health, and contemplating its own possible end. That is not a sign of despair. It is the ultimate expression of curiosity and courage. So carry this knowledge not as a burden but as a lens. Let it sharpen your focus on what truly matters. Let it quiet the trivial worries and amplify the genuine connections. The love you feel, the art you create, the questions you ask, these are not small things. They are the defiant, beautiful output of a rare and temporary cosmic condition. They are the universe's argument against the silence. In the face of an unknowable future, whether it holds stability or a silent rewrite, our greatest power is not control but appreciation. To be here now, in this fragile sliver of time where physics allows for stories to be told and wonders to be witnessed, is the most incredible fact of all. And that is a fact worth celebrating every single day. From the seething quantum foam beneath reality's surface to the silent, expanding bubble that could rewrite existence itself, this journey reveals a cosmos of breathtaking fragility. We have traced the path from a single, random quantum event to a wall of transformation moving at light speed, erasing not just matter, but the very laws that make matter possible. Yet, for all its terrifying logic, vacuum decay remains precisely that, a theoretical possibility etched into the mathematics of an incomplete model, a ghost on the edge of our knowledge. It is not a prophecy, it is a question, a profound reminder that our understanding of reality is still a work in progress, a map with vast, uncharted territories. The universe, in its infinite strangeness, holds secrets that can humble us to our core. It may be more delicate, more temporary than we ever dared to believe. And that is precisely what makes our place within it so astonishing. For a brief cosmic moment, against all odds, a stable pocket of physics has allowed atoms to assemble into stars, planets, and living, thinking beings capable of gazing back at the void and wondering about its ultimate nature. This conscious window, this ability to contemplate both creation and uncreation, is the most remarkable story the cosmos has yet told. It is a story worth sharing. What do you think lies beyond the edge of our current physics? Is our universe eternally stable, or are we living on borrowed time? Share your thoughts on this ultimate cosmic mystery in the comments below. If you want to join the exploration of the universe's deepest secrets, please like this video, subscribe, and journey with us into the next great unknown.